Okay, thanks for the introduction. So yeah, I'm a final year PhD student at CMU, and I work with Jan Hoffman and Frank Fenning. And today I will be talking about some of the work that I've done during my PhD. So as part of this talk, I will first explain kind of at a high level what digital contracts are. Then I will explain what resource-aware session types are, why I designed them, and how they can be used for programming these digital contracts. So let me start with like a very high level overview of what digital contracts are. So these are essentially just simple programs which enforce some kind of a transaction, often between distrusting parties. And these transactions are typically executed by third-party miners who store the output of these transactions on a global ledger, which is also known as the blockchain. And the user who generally issues the transaction typically pays for the execution cost of the transaction. And how is this execution cost computed? Well, there's a set standard which assigns a cost to every operation. And then the total cost of the transaction is just the sum of the total cost of all the operations that executed as part of the transaction. So the execution model looks something like this. The user submits a transaction along with some money, which is also known as gas, to the miner. The miner then executes the transaction, and if successful, adds the transaction to a new block, adds this new block to the blockchain. So the blockchain is nothing but a chain of blocks of transactions. And if the user provided excess gas and there is some leftover, then it is returned back to the user. And more importantly, if the user does not pay sufficient gas to cover the execution cost, then the whole transaction is aborted and the user has to reissue the transaction. So it is very important that the user knows exactly how much gas is going to be consumed by the transaction. Okay, so I want to take a very simple example of, let's say I'm running an auction on a blockchain where I'm auctioning this Mona Lisa painting. And suppose there are three bidders in my auction, bidders 1, 2, and 3 with their respective bids. So what would be the protocol of such an auction contract? Well, first, each bidder is going to submit their bids to the auction. And then at some point, the auction will stop accepting new bids. So its status, which is currently running, will transition to ended, indicating that it has stopped accepting new bids. And then the contract will determine the winner of the auction. So suppose in this case, bidder 3 is the winner, bid 3 is the highest bid. Then the Mona Lisa painting is transferred to bidder 3, and bids 1 and 2 are returned back to their bidders. And then the whole contract will terminate. So this is how like typically an auction contract would look like. And if you were to implement this and deploy this on a blockchain, you would typically do it in this language called Solidity, which is kind of the most prominent smart contract programming language out there, specifically designed for the Ethereum blockchain. And the contract will be executed using these two functions. The first is the bid function, which handles the bidding phase of the auction in which the bidders place their bids into the auction. So here you compute the value of the bid and the address of the bidder. You store it in a local dictionary called pending returns, which is stored at the auction. And you check if the bid is greater than the highest bid, then you update the highest bidder and the highest bid. So that's the bidding phase. And then there's a separate collection phase where bidders will collect their wins or losses from the auction. So here, the first thing is that you require that the sender is not the highest bidder, because the highest bidder will not get their bid back. They will get the Mona Lisa painting instead. And then you look up in the dictionary to see the amount that needs to be returned back to the bidder, and you send that amount back, and then you just return. So yeah, any questions about this before I move on? Okay, good. All right. So let's focus on this collect function for a second. I'm claiming that there's actually a bug in this code. Can somebody identify it? So let me give you a hint. So what happens if the collect function is actually called when the auction is still running. So it doesn't really matter exactly what's happening, but the important point is that the auction has a predefined protocol. First, all the bids must happen, and then all the collects must happen. And so the high-level problem here is that there is no way to statically enforce this protocol in Solidity. The workaround that Solidity has is that you can add a requires clause that status must be ended at this point, at the status variable, but there is like, and this will be checked at runtime, but there is no static support for enforcing these protocols. So the high-level problem, so to speak, is that all these contracts that typically have a predefined protocol, but in programming languages like Solidity, there is no way to statically enforce them. Okay, so now let's say I added require status must be ended. I'm claiming that there is still a bug in this code. Can somebody identify that? So let me give you another hint. So what happens if the collect is actually called twice by the same bidder? So here, as you can see, they will get their money back twice, and if the collect is called n times, they will get money back n times. And the problem here basically is that I did not update the dictionary to set pending returns of the sender to 0. And so the high-level problem here is that assets like the Mona Lisa painting or money, they are linear, but there is no support from the programming language itself to enforce this linearity constraint. It's up to the programmer to carefully program these contracts and ensure that money is neither duplicated or discarded in these transactions. But the language itself does not give any support. Okay, so now let's say I updated pending returns of message.sender to 0. There is actually still a bug in this code. And this one is a little bit more specific, so I'm just going to give the answer here. So the send function that you see here, which transfers the amount to the bidder, that not only transfers the amount, it also transfers execution control to the bidder. So it basically calls what is called a fallback function in the bidder's code base. And if the bidder chooses to call collect inside that fallback function, basically collect will call send, which will then call collect, which will then call send. And there will be this infinite callback, which will transfer all the money from the auction to the bidder until the auction contract runs out of funds. And so the way Solidity gets around this problem is by basically showing a guideline. It's not really enforced by the language, but a guideline that send should be the last instruction in your code. And so even if, so basically if you update your dictionary before you do the send, even if you have an infinite callback in all the subsequent calls, you're only going to send 0 money to the bidder. And so they don't really have an incentive to do this infinite callback. And this problem might seem like a little too specific or maybe benign, but this is what is called a reentrancy attack. And this is actually a very, very common source of attacks on smart contracts on the blockchain. The most famous one is the DAO, which was attacked in 2016 for $60 million. Based on just this simple vulnerability, but it has come up in more recently in other contracts as well. Okay, so now suppose I made send the last instruction. I updated the dictionary before the send. Hopefully this code is correct. I haven't really deployed it, so I don't know for sure. But now we go back to the original question I started with, which is how does the user compute the gas consumption of this transaction, because they need to pay that cost up front, that gas cost up front. And so you need to somehow statically estimate this resource cost. And currently the way to do that is by basically referring this EVM cost model, which basically stands for, which basically specifies the gas cost of every EVM bytecode instruction. So you compile this high-level Solidity code to EVM bytecode, and then you sum up manually what is the gas cost of every code instruction, and that's the total cost of your transaction. And so that's manual, it's tedious, and it's prone to errors. So this calls for some kind of like automatic resource analysis so that we can automatically infer the gas cost of these transactions for the user. Okay, so my claim is that resource-aware session types can actually help with all of these problems. But to see that, I want to revisit the auction protocol for a second, and kind of see what the protocol looks like again. So as I said, the auction has two separate phases. The first is the bidding phase. The bidder sends the ID, sends some money to the auction, and then the protocol recurses back so that more bidders can place their bids in the auction. And then there's a separate ended phase where the auction has ended, and the users can collect their. So the user sends their ID, and the auction returns back either the Mona Lisa painting or their money back, depending on whether the bidder won or lost the auction. And then the protocol recurses again so that more bidders can collect their wins from the auction. So my core idea here is that this auction protocol that I'm showing here, I will basically represent it as a session type. And then the type checker will enforce that this protocol is maintained by the contract that you implement. So this is what the session type that the auction protocols would offer. And this is a little bit complicated, so I'll go through this slowly and step by step. So as you try to see this type kind of from the point of view of the auction. So the auction is the provider and the bidder is the client of this auction. And so as you can see, the type starts with this plus symbol, which basically stands for internal choice. So what that means is as soon as a bidder starts interacting with the auction will either send the running message if the auction is running, or send the ended message if the auction has ended to the bidder. So it will indicate its status as soon as you start interacting with the auction. Let's say if the auction is running, then the type transitions to external choice, this ampersand symbol, which is the dual to internal choice. So in internal choice, it was the auction's choice to send one of these two messages. Now it's the bidder's choice to send one of the messages. And here there's only one option. So the bidder sends the bid message, indicating that they want to place up the auction. Then, so that message is received by the auction. Then the auction receives the ID for the bidder and the money that the bidder sends. And then the protocol recurses back to the auction so that more bidders can place their bids in the auction. So here, one thing that you will notice that ID is followed by an arrow, but money is followed by a lolly symbol. And that's because ID is a functional quantity, so it can be duplicated or discarded. Money, on the other hand, is a linear quantity. So it cannot be duplicated or discarded, only exchanged between different parties or different bidders or different contracts, but it cannot be duplicated or discarded. So this is to indicate to the type checker that you better treat money linearly. So that's the running phase. In the ended, the contract offers a choice to collect. So it receives this collect message, basically signifying that the bidder wants to collect their wins. Then it receives an ID, and then the type transitions to a plus again, so an internal choice again, which basically means that the auction will either send the won message if the bidder won the auction, or the lost message if the bidder lost the auction. In the case of won, we'll see this Mona Lisa tensor. So that means that the auction will send the Mona Lisa painting. So the tensor here is the dual to lolly. In the case of lolly, I was receiving, or the auction was receiving money. In the case of tensor, the auction will be sending the Mona Lisa painting. And then the protocol recurses back to the auction. Whereas in the lost branch, the auction will send some money. And again, these Mona Lisa and money, these are linear quantities, and that's what the tensor indicates. And in either case, the type then recurses back to auction so that other bidders can collect their wins from the auction. So any questions about this before I move on? Okay. All right, so that's all I wanted to say about the motivation for using session types. Let me give a brief outline of the talk. So I will start by first give a very brief introduction to session types. Then I will switch to talking about resource-aware session types and how they can be used to do work analysis. Then very briefly, I will talk about temporal session types and how they can be used to do span analysis. And then finally, I will talk about how resource-aware session types are used to program these digital contracts. And I'll then conclude with some future work. So let's start with session types. So what exactly are session types? They're basically a system for implementing these message passing concurrent programs. All the communication in these programs happens through bidirectional channels, and these channels are typed. And the type of these channels, which is what is known as the session type, basically enforces some kind of communication protocol between the different processes. So very similar to how the auction type was enforcing some kind of protocol between the auction and the bidder of the auction in the auction. So as a simple example, consider two processes, P and Q, connected by a channel. Now every session type channel has a unique provider and a client. So here P on the left is the provider, Q on the right is the client, and I usually indicate the provider with a blue dot on their end of the channel. And as I said earlier, every channel is typed. So suppose the type of this channel C is bits, which is basically defined as an internal choice. So that's the plus symbol between B0 and B1. And in either case, the type recurses back to bits. So what this type means, what protocol does this enforce? Well, because it's an internal choice, it's the provider's choice or P's choice to either send B0 or send B1. And then because the type recurses back to bits in either case, P again send either a B0 or a B1, and again forever. So P will essentially send an infinite stream of B0s and B1s to the client process queue. So that's the protocol enforced by this very simple type. Yeah.
Is there actually a difference between the provider and the client, or is there any particular reason why they're one way around or the other? Is the provider only allowed to send and the client only allowed to receive, or vice versa, or can they do both?
No, so the channels are bidirectional, but the way these intuitionistic session types are set up is that the client kind of exists first, and then it can create a provider. So like think of the provider as like a child process for the client. And so the client has to exist first before the provider. So that's one difference. And there is an asymmetry between how the channels are perceived. So if you look at the type, so here you have a plus internal choice. So that means that if you look at this type from the point of view of the provider, it means the provider has to send. If you look at this type from the point of view of the client, it means the client has to receive. So based on whether you are the provider on the channel or the client of that channel, the actions are dual depending on what type it is. So there's, yeah. Does that answer your question?
Partly. The related question then is, do you allow the creation of new processes, or are you just talking about statically having?
No, you can create new processes. So at any point in time, any process can kind of create a child process. And every time you create a new process, you basically create. So for example, here Q could have created this P process earlier. And every time you create a new process, you also get a unique channel connecting you to the new process that you created. That's how it
works. Right, and then at that point, the provider might be the client of a different provider.
No, so these channels are linear, which means that every channel has only two endpoints.
The channel has two endpoints, but processes can have multiple channels.
So every process can be a client for multiple channels, but it can only provide a single channel. So that's the constraint. So every process, like for example, the process P, because it's providing this channel C, it cannot provide on any other channel. It can use a bunch of channels, but it can only provide a single channel. And what this basically would mean is that the processes will form some kind of a tree structure where every process has connected to the parent by a channel that it provides on and uses a bunch of channels in its as its children.
Okay, thanks.
All right.
For stalling you.
No problem. Yeah. And so as a slightly more complicated example, let me take this queue data structure and talk about the session type for the queue. So here the type kind of starts with an ampersand, which is an external choice. So the queue offers the choice to either insert or delete. So it can receive one of these two messages. In the case of an insert, it receives an element of type A, that's the lolly, and then the type recurses back to the queue. So the data structure behaves as a queue again. So in this example, suppose I have these 4 elements, A, B, C, and D stored in my queue. To insert another element, I basically send the insert message and the element E, and then that element gets inserted all the way to at the end of the queue. And then because the type recurses, the data structure behaves as a queue again, so it can accept more insert and delete messages. So that's the insert branch. In the delete branch, the type transitions to an internal choice again, so plus, between none and some. So that means that the queue can either send the none message if the queue is empty, or send this, and in the case of none, it will then terminate, which is indicated by the type 1. Or it can send the some message if the queue is non-empty, as is the case here. Then it will send an element of type A, and then the type will recurse back to the queue. So the data structure behaves as a queue. So here, if the queue receives this delete message, then it sends back some followed by the element A that's at the head of the queue. And then because the type recurses, the data structure behaves as a queue again, so it can accept more inserts and deletes. So that's the interface that a queue data structure will basically provide to a client. So any questions before I move on? Okay, good. So that's all I wanted to say about session types. We'll keep coming back to it. Now let me briefly talk about resource-aware session types and how they can be used to do work analysis. So before I talk about resource-aware session types, I just want to, at a high level, talk about resource analysis in general for concurrent programs, which is what session types implement, because they differ a little bit from resource analysis for sequential programs. So for concurrent programs, there are 2 measures of execution time. One is called the work, also known as the sequential complexity, which basically stands for the total number of operations that are executed, total work done in some sense by each process or each processor in the system. And it doesn't really take into account the parallelism in the system. So if you were to sequentialize the whole computation and execute it on a single processor, then the total time taken on that processor will be the work. So that's one extreme. And the other extreme is the span, where you basically assume that you have infinitely many processors. So everything that can happen in parallel will happen in parallel. And then the total time taken for such a computation to take place with these infinitely many processors is known as the span. So if you have typically a fixed number of processors, then your time consumption will be somewhere between the work and the span. And there's like a Brent type theorem which can be used to connect the two. So in this talk, I will mostly be talking about work analysis, but if you're interested in the span analysis work or the time analysis work, you're welcome to read our paper at ICFP 2018 about that. It's called Temporal Session, Parallel Complexity Analysis with Temporal Session Types. Okay, so to focus on the work analysis, so let's go back to the queue data structure again and see if we can count the total number or the total work done by the queue, which I'm defining as the total number of messages that are exchanged within the queue data structure. So let's do that exercise both for insertion and deletion. So for insert, there are these two messages, the insert and the element E. These two messages travel all the way to the end of the queue where the element is inserted. So the work done to process this insertion is 2n, where n is the size of the queue, because these two messages travel to the end. Whereas for the deletion, the work done is just 2, because you just get two messages out, the sum followed by the element A. And so now you have to somehow statically express these work bounds. And so the way to do that is by what I call the potential method. So here the idea is pretty straightforward. All the processes, they basically store some abstract notion of a potential. It only exists at the type level to statically get work bounds, and it's not really needed at runtime. So it doesn't really create any runtime overhead. This potential can be stored in the processes, but it can also be exchanged between different processes via special messages. And this potential is kind of consumed every time you do some work. So what do I mean by work? Well, in the previous example, I was talking about the number of messages. So every time you send a message, you consume 1 unit of potential. But one strength of our system is that our type system is kind of parametric in the cost model. So the user can decide what they want to count. Like they may want to count the total number of functions called, or processes spawned, or arithmetic operations, or messages, or whatever. Once they decide the cost model, our type system is parameterized by it. And then the type system will return the work bounds for that particular cost model. And so that makes it a very good fit for the blockchain domain, where these smart contracts, every operation has a gas cost. So in the cost model, you basically specify the gas cost of every operation, and that will give you the total gas cost of the transaction. So this potential, as I said earlier, is consumed to perform work. And so basically what, at a high level, what happens is that the initial potential in the system, the total potential in the system, will act as an upper bound on the total that will ever be done by the system. And so that's how potential basically acts as an upper bound on the work in the system. So going back to the queue example, so how do you express these work bounds? Well, it's done in two steps. The first is that you introduce this index refinement, where you basically mark this queue with n, which stands for the size of the queue. And then you have as you can see, it's the size, because in the case of insert, it goes to q of n plus 1. In the case of delete, it goes to q of n minus 1. And in addition, there are these two left triangles of 2n and 2. These basically stand for potential annotations. So what does it mean exactly? Well, in the case of an insert, the queue receives 2n units of potential. And in the case of delete, the queue receives 2 units of potential. And internally, this potential is then consumed to exchange messages within the queue data structure. So the work done by the queue for an insert is bounded by 2n, and the work done by the queue in the case of delete is bounded by 2. And that's basically how you can transform, or you can translate these work within the types or the session types of the data structures itself. And that will give you a bound on the work for these programs. And so there's a whole body of work that I've done on how the meta theory and the implementation of these refinement session types work. And so I've referenced the below, and we have also implemented that in an open source repository. So you're welcome to look at that. Okay, so just as a simple application of resource-aware session types, I'm showing here the type of a stack versus the type of a queue. And if you closely look at the type, then you'll see that there is no difference between the interface, because the stack and the queue interface is exactly the same. The only difference is in their work bounds, in their potential annotation. So now, just looking at the type, can you tell me which one is more efficient? Yeah, so here, as you can see, in the case of an insert, the stack does not need any potential, whereas the queue needs 2 units of potential. Whereas for delete, in both the cases, you just need 2 units of potential. So now that's the power of resource-aware session types, is that just looking at the queue type or the stack type, you can infer its bounds or its efficiency. So without even looking at the implementation anymore, you can decide just by the type that stacks are more efficient than queues. Only in the case of an insert. So you get a very fine-grained analysis on the efficiency from the type. Okay, so that's all I wanted to say about resource-aware session types. Let me briefly talk about how they can be used to program these digital contracts. So the session type language that I've talked about so far, it cannot be directly used to program these digital contracts. And that's because of two limitations. One is that the channels, they are completely linear. What does that mean? Basically, every channel can only have two endpoints. And in particular, let's say the channel that was offered by the auction can only have one bidder, can only be connected to one bidder. And then that auction will only have one bidder, and then it wouldn't really be an auction anymore. So to incorporate multiple bidders, you need to somehow share the auction channel between multiple bidders, which is not really allowed by the current work on session types, or at least the standard work on session types. So that's one limitation. The second one is the language I was talking about so far, it doesn't have any functional layer. There are only channels. So in particular, the auction cannot have lists of players or the mapping from the players to bids. It cannot store any integers or booleans or anything like that. And so that kind of precludes any general purpose programming. And so to do some kind of real world programming, I need to integrate these session type languages or the session type language with a functional language. And fortunately, both of these have been explored in prior work, but they were never combined. So my language is kind of the first one to combine these two together. So I'll talk about them step by step. So first, let's talk about sharing of channels. So this is very recent work done by my collaborators. Here, basically, the idea is that the types are stratified into two layers. So there's a linear layer and there's a shared layer. And there are modal operators connecting the two layers. So in particular, there's an upshift operator, which shifts a linear type to shared. And there's a downshift operator, which shifts a shared type to linear. So programmatically, what this translates to is that the auction basically has a shared channel that is offered to all the different bidders. And to interact with the auction, you need to first acquire that shared channel. Kind of works very similar to shared memory. So this channel you acquire, if that acquire request is successful, you get a linear reference to the auction, so that you can use that channel to that linear channel to interact with the auction, send your bid or collect your bid or whatever. Once you are done with your interactions with the auction, you can then execute a release request. And then if that release request is successful, you will lose the linear reference to the channel. The channel will become shared again so that other bidders can acquire the channel and interact with the auction. And one kind of key limitation of prior work was that shared processes like the auction, the processes that offer shared channels, they could not store any linear assets. So in particular, the auction cannot store money, it cannot store the Mona Lisa painting, and then it wouldn't really be like an auction anymore. So for our language to work on a blockchain, it was very, very important that these shared contracts, they basically are able to store linear assets. So this was kind of the most technical challenge of my work, on how can we overcome this limitation without compromising type safety. But I mean, in the interest of time, I'm not going to talk about that, but you're welcome to read our paper to see more details on that. And this technique of acquire release is actually the one that prevents reentrancy attacks, because what you can show is that to attempt reentrancy, which was this infinite callback, you basically will have to acquire the contract and then acquire it again without releasing it. And then what would happen is that the acquire would fail and the whole system would deadlock, and we have a deadlock detection mechanism built into the language, which will detect a deadlock and then abort the whole transaction. But more importantly, this infinite callback, which basically depletes all the money from the auction to the bidder, that would not happen. And so that attack is prevented kind of by design by our language. Okay, so that's all I wanted to say about sharing of channels. Now, very briefly, the integration with a functional language. So this was also done recently by some of my collaborators. So here the idea is that the session type language is basically integrated into a functional language via a linear contextual monad. And the idea there is that the functional data structures, they're basically completely isolated from the session type channels. And there's very limited interaction between the two. And in my case, because I want to do resource analysis on top of everything, I had to integrate resource-aware session types, which is what I designed with resource-aware ML, which is also recent work that I did with some other collaborators. Okay, so resource-aware ML is basically a functional programming language with support for resource analysis. So now that we can do resource analysis at both the layers, the functional as well as the session type layer, we can kind of do resource analysis in the whole language. Okay, so with all these parts introduced, this is what the final auction type will look like. So the first thing to note here is that these left and right triangles, they are marked with these star annotations. So that's one kind of advantage or feature of our type system, is that the programmer only needs to mention where exactly potential needs to be exchanged between the different processes. The exact potential that needs to be exchanged, that is automatically calculated by our type checker based on the execution cost of the program. So for the implementation I chose, the numbers turned out to be something like this. And so what does this type exactly mean? Well, the type starts with an upshift. So it means that the auction type is initially shared. So it must be acquired to be used by a bidder. So that's the upshift. And then as soon as you acquire the contract, you have to send 22 units of potential, which is received by the auction. So that will be used internally by the auction to pay for the execution cost of the transaction. And then depending on which branch you take, different branches have different execution cost. So let's take the running branch, for example. Here, once their transaction has kind of ended, towards the end, there's a leftover of units of potential. And so that's what this right triangle 7 indicates, is that at the end of the transaction, whatever is the leftover potential, it is sent back to the client or the bidder in this case. And so this works very similar to how I was showing the execution model on the blockchain, where you initiate the transaction with some initial gas, and then the leftover gas is returned back to you. So here, that information is basically pushed to the type level, where you initiate the transaction, or in this case, the session type, by paying some potential, and then the leftover potential is sent back to you. And once all of that is done, there's this downshift, which basically indicates that, okay, once you're done interacting with the auction, you must release the auction contract so that it can be used by other bidders in the auction. Okay, so that's what the shared auction looks like. Sorry, was there a question?
Hi, yeah, I do have a question. Can you just go back to the preceding slide for a moment? So, right, this is very precise information, which is nice, but I'm slightly confused. Instead of requiring 22 units and returning 7, couldn't it just require 15 and not return anything?
I mean, in some cases it might be possible, but in this case, statically, you wouldn't know which branch you are taking. So in particular, if you take the ended branch, or like where the Mona Lisa is sent, you will see that there is no potential that is sent back. There is no right triangle on that branch. And so that's why, because the cost of that branch is 22.
Okay, that makes sense. Yeah. Okay, yeah. Right. So in the worst case, there's nothing to return.
Right.
And hence, in the other cases, you would have to return something. Now I understand. That's much clearer. Thanks.
Okay, sure. Thanks. Okay, so as one kind of last thing, I just wanted to show a little bit of session type code. So here I'm basically showing the code for the running phase of the auction, where you are basically bidders are placing their bids in the auction. So here there's this run process which stores the list of bids in the variable B, the total money in the variable M, the Mona Lisa painting in ML, and it offers this shared auction which has this auction type, so the channel SA. And so here you will see how closely the code correlates with the actual session type itself. So the first thing that you do is that you accept an acquire request, which corresponds to this upshift in the type. So you accept an acquire request. As soon as you accept it, you send the running message saying that the auction is running. Then you receive the bid message. So you case analyze on that channel. You receive the bid message. Then you receive the ID and the money in variables R and M. And then you basically detach from the client, which matches like the release request. So that's how the interaction happens between the auction and the client. And then internally, you add the bid and the money. So you will see how closely all these interactions are basically expressed in the session type. So once you are able to write the session type for a process, it's actually very, very easy to write the code also. Another thing that you will see is that there are no work constructs like receiving potential, paying potential, consuming potential to do work. Those kinds of things are internally inserted by the type checker itself. So the programmer basically can remain oblivious to the exact cost of different operations. They only need to mention these right and triangles, and that too only with a star. So they can kind of remain oblivious of exactly how much cost is consumed during execution. Okay, so just to kind of conclude this section, I just wanted to contrast existing languages like Solidity with the language that I'm proposing, which we call Nomos. So for starters, the protocol is not explicitly expressed in Solidity. There's no support for that. It has to be enforced somehow through these assertion checks, runtime assertion checks, whereas in Nomos, the session types, they nicely express the protocol, and the type checker enforces these protocols. Again, in Solidity, there is no support for analyzing resource usage, whereas in Nomos, there are these resource averts which express the gas usage. In Solidity, there is no way to enforce linearity of assets, so the programmer has to carefully ensure it manually. Whereas in Nomos, there is a linear type system because session types are inherently linear. And so that can be used to track assets like money and Mona Lisa. And finally, Solidity contracts are prone to reentrancy attacks, whereas in Nomos, you cannot have any reentrancy. That's eliminated by design. So that's all I wanted to say about programming digital contracts. Let me just conclude with some future directions. So one thing that I wanted to try is how can we actually track time as well in Nomos, because there are some contracts, for instance, the auction, that are time specific, where we say that, okay, the auction will stay open for 5 days or something like that, and then it will close. Can I somehow represent that information statically and enforce that through type checking? And I've already worked out, I talked about this very briefly, but I already worked out how to express time with session types. And I want to see how much of that I can incorporate in Nomos language. Another thing that I talked about just now is that the programs, they closely correspond to their session types, the interaction part of it at least. And so one direction is, once given the session type, can I synthesize the programs automatically? Another point that I talked about very briefly was about refinement types. So I talked about like how refinements work with session types, and I'm seeing if I can integrate that into the Nomos language through some kind of application smart contracts. There are still some open problems with respect to integration with blockchain. For instance, so far I only talked about cost models that are constant. Every operation has a constant cost. But what if there are more generic cost models where the cost of an operation depends on the value of the or the size of some data structure or something like that? Another thing that I'm trying to do is the compiler for Nomos to Ethereum WebAssembly, and so actually deploy some of these contracts on the Ethereum blockchain to different practice. Another thing that I talked about was that I have a deadlock detection technique built into the language, but I do not have any deadlock prevention technique. So I cannot like give a feedback to the programmer that, hey, your program might deadlock here, so pay attention to that. So I'm looking into, in the future, how can I do like static and dynamic deadlock prevention also with session types. So just to conclude, I talked about today resource-aware session types, how they can use to track sequential complexity using the potential method, and then I talked about how they can be applied to implement these digital contracts. And the guarantees that they give are enforcing protocols, tracking gas usage, enforcing linearity, and preventing reentrancy attacks. And all of this Nomos is implemented and available open source at this GitHub repository. And very recently, I'm pretty excited about this, we also released a web interface for this language at this URL. So you can actually go and without even installing anything, you can just play with the Nomos language, write your own transactions. I actually have some predefined transactions in there already, and run them and see how it works in practice. So with that, I come to the end of the talk. Thank you.
Thanks. You'll see the chat window. People are thanking you. Petros, please go ahead.
Yes, hi. Thank you for the very interesting talk. I actually have a lot of questions, but I'll try and ask only two. So the first one is quite specific. So I'm not sure I'm understanding this 100%, but what prevents a malicious user to introduce a client protocol that doesn't follow the type, so that, for example, they bind into the protocol and never release it, into the contract and never release it? Wouldn't that block the whole process?
No. So there's a couple of things there. So first is that every time a client wants to bid in the auction, what they will have to do is they will have to submit their bidding code. And what the type checker basically does is that it looks at that code and sees if the session type that the client is using matches the session type that the contract is offering. So that's one thing. The second is, well, what happens if you acquire a contract but never release it? So one thing is that once you acquire something, you basically, it transitions from shared to linear. And so if you acquired, let's say, a shared contract, so for example, if I show the code here, right? So here you basically kind of, so this is the provider side code, but the client side code will look something like this. It will here acquire the auction channel, and here it will release the auction channel. If you do not release the auction channel, you basically have a linear channel in your context, and you cannot terminate until you release all the linear channels. You cannot terminate holding a linear channel in your context, basically. That's enforced by the type checker. So you are guaranteed kind of by the, like if you have a terminating, well, I mean, basically if you have a well-typed code, you are guaranteed that every channel that you acquire, you have to release in the end.
But if you're still translating to Ethereum, right? To the Ethereum, what's it called, the machine language?
So that part I haven't done yet. We haven't. So the way the system is working right now is that if you look at like the web interface or something, is that we have like a kind of a simulation of a blockchain running in the background, and every time, maybe I can actually show that. So let's see, how can I actually do that? So if I wanted to share, yeah, okay. So if I see, yeah.
My point is that if you're translating to a host language that is not type checked, then people can bypass your type check.
Yeah, that is definitely true. So if we are translating to a host language, that wouldn't work. But if so, right now all of this is happening in the source language, and that's kind of another thing that we are looking at is how can I have like nomos or contracts implemented in nomos interact with contracts that are implemented in a different language, and how it would look like to compile it down to some other. Yeah, but right now, like if you want to like so for example, this kind of yeah, so you check this transaction, and then it will say, okay, type checking successful, and then you can actually create some account and then actually submit the transaction, and then it will say, okay, transaction successful or something like that. And then if you want to actually this is, for instance, what the user code will look like. So here you acquired the channel, and here you release it. So suppose I don't release that and see if I try to type check it, it will say, okay, type error, linear context is not empty when you're basically terminating. So it will give you, when you're trying to terminate, when you're trying to close, it will give you like a type error. So that's one thing. And yeah, so once we go down to like a source language, these things will become a problem. So yeah, that's something, or to a kind of a low-level language. We have to see how that would work.
That's right. Thank you.
Okay, we'll go in order. Vasco, please.
Hi, nice talk. So is Nomos supposed to run on the blockchain side or on the client side, or both?
Both. Right now, both.
Right. And so,
yeah.
So I think my other question was partially answered. So the model is such that because in Ethereum, clients are just JavaScript programs, so you can do whatever you want, right? But in this,
right.
your model is such that your clients will have to somehow upload their script, right? That is checked by the blockchain and run at the blockchain, right? That's the idea.
Right. So there is like one additional layer of type checking that happens at the client level also, which can kind of basically, that's the one that gives a lot of guarantees about like linearity and reentrancy and things like that. Yeah.
Okay. Thank you.
Sure.
Thanks, Phil.
Hi.
Hello.
Just turning the camera on. Right. Hi. Thank you. That was a really interesting talk. People have touched on this, right? But ultimately, you might compile to something like Ethereum and run on Ethereum. You'll need to solve various problems before you can do that.
Yeah.
I wanted to encourage you to look at that practical direction. I mean, there's lots of interesting theoretical stuff for you guys to do. I hope you'll keep doing it. But providing a compiler from this to Ethereum so people could actually experiment with it, I think would be a great idea and probably throw up some new issues. So I just want to encourage you to look at that direction.
Yeah, sure. Yep, thank you. I will.
And of course, one of the important things you'll need to do that is the open problem you mentioned, which is right now you can deal with constant costs, but not with costs that depend on the size of the data structure that you're dealing with.
Right.
And those will be important.
Right.
As well as directing you to Ethereum, you might know that I work with IOHK and we have a blockchain called Cardano.
Yeah.
One of the interesting things about Cardano is that it's not based on an account model like Ethereum. It's based on what's called a UTXO, unspent transaction output model, just like Bitcoin. And that's a bit more functional. Turns out to have some interesting advantages. So when you submit a transaction to Ethereum, in general, how much it costs, how much gas you need, depends on what's currently on the blockchain, which depends on which other transactions got there before yours. So there's no way of knowing exactly what it's going to cost in advance, depending on what the history of things is.
Right.
With UTXOs, you say, right, I'm relating to exactly these transactions. It's something much more familiar to functional programmers. As a result, the cost only depends on the data in those other transactions. So at the time you submit your transaction, you know exactly what it will cost. So that's a nice advantage.
Right.
And so it'd be interesting, as well as for you guys looking at how do we fit this into an account model like Ethereum. I'd also be very interested if you looked at how do we fit this into a UTXO model, which might in some ways be easier because it's a bit more predictable in some ways.
Mm-hmm. Yeah. I mean, one kind of advantage that we provide with Nomos and in general with these resource types is that we allow amortization as well. So what you can do is you can actually store potential inside the data structures, in particular inside these UTXOs, which can be used to pay for the execution cost of the transaction, even if you have like some cost models that are costs which are dependent on the sizes of the data structures. The data structure itself will have the potential to pay for it.
Right, and that's a nice trick. I think that trick might work well both for account-based and for UTXO-based models.
Right.
So I just want to mention it might be interesting. And of course, if you do want to do that and we can help you out, let us know. We'd be really happy to collaborate with you on something like that.
Sure, sounds good. Thank you. I will reach out to you.
Okay, and thanks for the talk. It was very interesting.
Thanks.
Thanks. Matthias?
Yeah, thank you very much for the talk. I just had a quick question about sort of the separation between runtime and what you statically check, because it seemed to me that the gas cost was sort of a runtime concept. That is where you check that you have enough gas, but you check statically the cost of doing something.
Right. So go ahead.
So the guarantees you get from a well-typed program using these session types is that under the assumption that you have this much gas in your account, you will succeed doing the operation.
Exactly. Yeah. So like here is a very good example of here. So if you see my screen here, there is this account in Frank's name which has this much balance, and I'm basically trying to execute this transaction get storage. And here you will see that there is a star marked on the turnstile, which basically means that, okay, please infer the cost of this transaction. So if you check elaborate, what will happen is that you will see, where is it here? Get storage function now has 6 units. So it basically inferred that, okay, this transaction get storage has 6 units of gas cost, and it says here as well, like the gas bound is 6. And then you can actually submit this transaction, and then you see that the balance was reduced by 6 units. So it was 9997, now it's 9991. And that's basically saying that, okay, as long as you have 6 units in your gas account, you will be able to successfully complete the execution of this transaction. If I had less than 6 units here, it will say, okay, not enough gas in your account to run this transaction. So that's kind of the advantages. Sorry.
I was just acknowledging that you do check it before running the transaction, so you do ensure that nothing will go wrong, but you just check it at another time.
Right. Yeah. So you're guaranteed that whatever cost by the soundness theorem of the language, by the preservation theorem, you're guaranteed that whatever cost is inferred statically, it will exactly be matched at runtime.
Right. Thank you very much.
Yeah.
Okay, last question from Sam.
Oops. I'm just trying to share my video. Okay, can you hear me?
Yeah, I can hear you.
Okay, good. Yeah, well, I have a couple of things. So first, just following up on Petros's question about whether you might forget to or fail to release a resource or something, and obviously the linearity prevents that from happening.
Right.
Am I right that there's basically no way of holding onto a resource for too long anyway, because you have the resource costs bounded. So
yeah,
you can't have kind of an infinite loop or something, right? Okay.
yeah, you cannot have that.
Okay, so that's good. That's good safety. And then my other question is about well, you mentioned deadlock.
Right.
So I'm interested both in potentially ruling out deadlocks, but then another thing you might sometimes want to do, although perhaps that's much less relevant in this kind of setting, is to rule out data races as in part of your protocol. Do you have any kind of analysis of either of these that you do?
Right. Yeah. So for deadlocks, what we do is so in particular, when you look at a transaction, if it runs successfully in this Nomos language, the kind of configuration, which basically refers to the set of processes in the system, it will have a specific shape. That okay, it must have these many processes or these many channels, no unconsumed channels, things like that. So there are some like a well-formedness invariance on the configuration if the transaction or function successfully kind of executes. It's very similar to how we say that an expression will either become a value or it will keep stepping or something. And when it becomes a value, there are some invariance on how it will look like. So that's what we do here also, is that when the kind of transaction, so I try to see if I can keep the expression or the configuration stepping. And once that stops, like if there is a deadlock, I will not be able to step the configuration. And so what I do then is that I see that, okay, does this look like the final configuration? Does this satisfy all the invariants that a final configuration satisfy? And if yes, then okay, transaction successful, everything is good. If not, I basically say, okay, there's only one reason that this transaction could have like not reached its like final configuration, and that's because it deadlocked in the middle somewhere. So that's kind of what we do right now. What we are looking into with respect to deadlocks is there are these distributed deadlock detection techniques. So for instance, there is this Mitchell-Merritt algorithm for distributed deadlock detection, where you say that, okay, once you have a deadlock, you basically try to identify the process that one of the processes that is in the deadlock cycle, and it will basically try to send a message which can try to release the deadlock or at least detect a deadlock. And that's one of the things that we are looking to implement into the Nomos language, some of these distributed deadlock detection algorithms. So that's what we do for deadlocks. For data races, we do not have anything particularly implemented because we are kind of guaranteed by the type system that only one channel will be, or one process will be acquiring a channel at any given time. So those things are kind of guaranteed by the type system. So in particular for data races, because we are only executing one transaction at a time, it's all kind of sequential. We don't yet support parallel execution of transactions. We don't really have like a data race specific problem right now.
And don't you have the situation, I mean, I just thought you'd want the situation where different clients might come along sort of non-deterministically, rather than just saying, oh, I have to let this person go first. Do you not have that situation?
So currently, so one of the things that's very important in a blockchain is that you want to have deterministic execution.
In the end,
so,
yeah.
Yeah. And so the way we do that, if I have multiple clients, there is basically a heuristic which chooses one of those clients, not at random, chooses one of those clients based on some heuristic. And then basically that is how like this non-determinism problem is resolved in the execution.
Okay, that sounds a bit worrying in the sense that maybe the clients could game the system to get an unfair advantage.
Yeah, so that's one of the things that we are working on right now, is that how can we prevent clients from gaming the system? Basically, the way we do it right now is that the channel, so it basically depends on some kind of ordering of, like, every process has a channel that it offers on. And so every client has their own unique channel that they offer on. And the names of these channels are determined at runtime. So no one can.
It's just run, so I'm going to have to disappear for a couple of minutes. Sorry.
Okay, no problem.
Phil has a question.
Just a comment on this last point raised by Sam. So very often, right, we think of race conditions as a bad thing. But there are times when a race is exactly what you want.
Mm-hmm.
If you're sharing tickets to something, then you want a race, right? Whoever gets to you first gets the last ticket. And I think many of the situations that we're dealing with in the kinds of applications that you look at on blockchain are things where you actually want to permit a race rather than want to outlaw races. And like when Kaka, my student, has spent a lot of time, she's been looking at, well, how would you have races if you wanted them in linear logic? Mm-hmm. So I think that's actually a pretty important problem. I'd encourage you not to ignore it.
Right. Yep.
Okay, Sam, are you back now?
Yep, just got back now.
Yep, go ahead.
Sorry.
Yeah, I'm just trying to. I kind of forgot what I was saying.
I think you'd almost finished saying what you were saying anyway, about gaming the system.
Right. Yeah, right. So right now what we have is there is, like, every process has a channel associated with it, and there is no way for you to, like, determine what channel will be associated to you. Those channel names are kind of randomly, not really randomly, but there are internal heuristics which generate those channels, and you don't really have a control on what channel name you will get. And that's how these deadlocks or these non-determinisms are resolved. And so, like, but that is, like, an interesting question for sure, is that making completely sure that there is no way to game the system. So that's something kind of for future work.